Welcome to the final virtual event of 6GTWINS project. The project was funded by the Minister of University and Research in Italy, and it has the focus to study network digital twins application in modern networks. My name is Fabrizio Granelli, and I'm full professor at the University of Trento and coordinator of this research project. This final event is structured in terms of different presentations, so I will go first to introduce the concept of digital twin and a few findings that we demonstrated, and then I will leave the floor to my colleagues for additional details. So let's get into the main topic and start understanding what is a digital twin and what is a network digital twin. First of all, let's look at the perspective. We put the network digital twin in the perspective of the evolution of the mobile networks from 5G to 6G, since we believe that that is a proper environment, as also I will explain you later, for the implementation of digital twins. The thing is that 6G is expected to improve on 5G, not only in the performance in terms of data rate, reliability, latency, and so on, but also in the functionalities. And this involves not only following up from 5G on network function virtualization and software-defined networking, but also integrating new technologies such as AI and machine learning and additional autonomous strategies to make the network management quicker and less expensive. If we look towards 2030 on the ETU plan, we can see that if 5G is the small triangle, the green triangle in the middle of this slide, then 6G extends its functionalities by deploying immersive communications, hyper-reliable and low-latency communications, as well as have massive and machine-type communication scenarios, but also it will increase with 3 additional scenarios that are integrated sensing and communication, AI and communication, and ubiquitous connectivity. This will lead to a technology that will not only be able to connect the unconnected, but also to be secure and reliable, to bring ubiquitous intelligence in networking, and also be sustainable. What is then the digital twin? So why are we speaking about digital twin in this presentation? Well, a digital twin differs from a simulation or an emulation environment because it does not only provide a virtual representation of a physical object in digital format, but also it includes accurate synchronization, so it is capable of providing an accurate and up-to-date picture of digital twin, and this is enabled by real-time updates that are continuously performed between the physical and the digital twin. So not only we have a physical entity that is transformed into a digital model, but we have a continuous data connection and in principle bidirectional connection between the two. And this allows to implement services on the digital twin that do not affect directly the physical entity, but they can ease the operation of the physical entity or the understanding of its nature. Digital twins are very famous for their application in well-known scenarios, like, for example, manufacturing, to enhance the efficiency, reducing the downtime to real-time monitoring and proactive maintenance. But also we have applications of digital twin that will be very promising in other areas like healthcare for personalized treatment, supply chain for optimizing logistics, construction to be able to better monitoring the buildings and the infrastructure, as well as in other complex system of systems such as the smart cities. So what is the main feature of the digital twin? The main feature, in my view, is the connection between physical and digital twin. Because to have a good data connection, it allows the digital twin to be accurate and provide a reliable replica of the physical system. Such link enables the users to analyze the current state of the object in the physical world, but also to perform predictions and understand how actions might interact with the physical entity. What happens if we extend this concept and we apply the concept of digital twin to networks? First of all, does it make sense? In our vision, it makes sense because this goes in a direction where all network innovation in this period are going. Because today, networks are improving their softwareization, they are increasingly become softwareized, they go towards higher level of automation, but not only that, they are also targeting higher integration of AI and machine learning to improve the performance and increase network management capabilities, and of course also sustainability, in the sense that networks are power-hungry devices and a component of today's digital society, and they need to be sustainable. So their energy consumption should be accountable and proportional to their relevance and their performance. Why to use digital twins then in networks? We have the capability to address all the innovation that were presented in the previous slide, because integrating network digital twins will enable to analyze scenarios, so to evaluate potential changes to the network and their impact before implementing them on the physical network. It will help to handle heterogeneity by ensuring integration and interoperability of diverse network elements, but also a network digital twin will improve the predictive capabilities, because we were able to extract more data and have increased forecasting capabilities, but also to include the capability for a network to be self-aware, because the network will have a mirror that will help itself to understand what is happening and its own status. And this will help to analyze, for example, what-if scenarios or analyze predictive actions in order to improve performance and support the required KPIs. In network management, of course, the digital twins have a lot of applications that are summarized here. Just to mention a few, the capability to perform precise simulation scenarios, to be able to work on proactive maintenance, anomaly detection, predictive analytics, demand forecasting, failure predictions, and so on. So the applications are potentially endless. So what is now the tools that we need for building the digital twin? We believe that a good tool to start with is a network emulator. A network emulator is a software environment that allows to replicate the protocols, the packets, and the services with high precision with respect to the actual infrastructure. So we decided to build our own version of a network emulator, properly packaged with functionalities that are required in order to get a suitable network digital twin. You can find our network emulator built in collaboration with the Technical University of Dresden at the link that you see in this picture. And we believe this is the right tool for implementing digital twins, because it merges the advantages of software-defined networking to design flexible, programmable networks and to enable real-time reconfiguration and agile programmability of the network, with the network function virtualization part that allows to deploy services easily based on Docker containers, to perform service migration, to implement advanced topological solutions like edge computing, and so on. So then we need a channel to interconnect the network digital twin with the physical twin. And in order to study this problem, we started implementing some approaches to collect data from the physical network and to perform predictions within the digital twin. In order to do that, we implemented some neural network-based approach, like this that you see in this picture, where we implemented a convolutional neural network to perform time series forecasting of network traffic, with the idea to study which is the proper look-back horizon that can be used in order to perform a proper prediction. So here we assume that we want to predict the next 1 minute of traffic in our network digital twin, and we wanted to understand which is the look-back period. So how much should I look in the past to have enough data to perform an accurate prediction? And you see here that if you use 1 minute of history, you can predict 1 minute in the future with a relatively good accuracy. But of course, if you go to more time backwards, so if you go to, instead of 1 minute, to 3 minutes and 5 minutes, as you see in the right part, you can get a higher performance. Of course, as you can see, the advantage of having more and more data decreases over the time interval. So we believe it's not necessary to look so much in the past in order to have a reasonable prediction, because this can be done with a few minutes of history, and then the incremental advantage becomes smaller and more small. So here you can see the corresponding improvement if we use 3 minutes and 5 minutes of historical data respectively. Of course, accuracy increases always, but you see that the prediction, that is the red curve, is extremely similar in both cases. So what we can say is that it's important to properly balance between how much we look in the future and how much we want to look in the past, because looking in the past increases the complexity in our system and the complexity of the prediction, sometimes without improving too much our capabilities, our performance, while on the other side, looking too far in the future can be problematic because it can lead to prediction drifts in case we look too much in the future. So we made some experimental analysis, and we found out that it is reasonable, unless we want to study a longer time series like weekly traces. It's enough if we want to understand the real-time behavior of the system to look a few minutes in the past and some minutes in the future. Then the problem becomes how we can reduce the playback time, so the time that goes between what happens in the physical twin to be replicated in the digital twin. Because normally this playback delay, as you see in this figure, is the sum of the time to collect the data, the time to analyze the data, the time to transfer the data to the digital twin, and the time to integrate the data in the digital twin. This leads to a fairly large synchronization time or playback delay. We believe that if we are able to properly predict the traffic, we can turn back the time, so we can start playing back from the future, let's say, in the digital twin, so that we can introduce a negative delay and reduce the playback delay to the minimum possible value, that is, in principle, even zero, if we continuously and periodically collect data and perform continuous predictions. Then, of course, we need to be able to maintain stable predictions, and for this we need to have a continuous process to improving the estimate of and our prediction accuracy. And we propose to do this through PID integration, so to using a PID controller. As you see in this picture, the idea is that we will continuously receive data from the physical twin, and we will compare this data with our predicted values, so we aligned the time scale between the two, and based on the error that we get, we will use proportional, integral, and derivative corrections, so that we can have a more stable control signal to send to the prediction model to improve and adapt the prediction so that it is aligned to the actual data that we have. Here you can see the corresponding performance. That is quite impressive. It's we mostly halve the error simply by introducing this low complexity way to compensate for the error. We also decided to build a real network digital twin, and since we had to do it in the lab, we decided to use an Amarisoft Callbox Classic 5G private network that you can find as lab equipment. That is our physical twin. We built the network digital twin based on our network emulator, ComNetSemu, in form of a virtual machine. And we sent to the network digital twin the configuration of the user and the control plane. And then every 2 minutes, we sent traffic traces that are played back by the network digital twin. So you can find the software that we developed at the link because everything that we did is openly available to the community. So here is an example of accuracy. And on the top, you see what happens in the physical twin. On the bottom, what happens in the digital twin. The only change here is that we changed the time scale of the digital twin in order to align them because in our testbed, the network digital twin operates with 2 minutes delay because of the capturing time of the packet traces. But as you can see, the results are quite promising because the shape in terms of throughput of the traffic between the physical and the digital twin is extremely similar. So we can conclude that the accuracy is relatively high, also in a real deployment of the system. Then we also addressed a few additional points that we believe are interesting. One is who should develop network digital twins, in the sense that most available digital twins today are mostly open source. So they are built by the community based on models that are commonly accepted. However, even vendors could build their own network digital twins. For vendors, this could be different in the terms that they could build network digital twins as black boxes so that they can protect their own patented information or secret information, because the actual usage of the network digital twin is as a black box that we can use for optimizing its parameters and its performance. And it's not necessary to know all the internal details. The important thing is that the network digital twin should be accurate enough for our purposes. So this could open the floor for the capability, for example, of vendors to sell to customers not only the physical object, but also the related network digital twin to study it and to better understand its behavior. So moving forward, the next steps are surely to implement network digital twins in modern network architectures. 6G is a good candidate because it's the upcoming mobile network standard, and based on the combination of SDN and NFV present in 5G, this can be a proper strategy and a complementary technology that can be easily integrated. In general, the network digital twin can be useful for training AI and machine learning. Since today we are missing good data sets, the network digital twin is a potential source of data sets that can be used for training. Another thing is to perform proper prediction and modeling of systems, as well as to understand who will be the owner, so whether we will have black box, a white box, or a combination of those in terms of the actual digital twin property somehow. About standards, we contributed to ETSI in the ENI working group by proposing the integration of network digital twins within the experiential network intelligence architecture proposed by ETSI, and we collaborated to a proof of concept with ETSI Zero Touch Service Management Working Group to demonstrate, together with the ORS SNSJU project, how a network digital twin can be used for analyzing what-if scenarios in security applications. However, 3GPP is actively also studying how to integrate digital twins, as well as the Internet Engineering and the Internet Research Task Forces. For example, Internet Research Task Force has a dedicated working group that is called Digital Twin Network that is studying the interfaces and how to integrate network digital twins within future networks. So to conclude, we studied how to build effective network digital twins. In our case, we focused on 5G networks with a perspective to look into 6G in the near future. We demonstrated that network digital twins are a suitable technology, but still also it is still not complete and not mature, because additional topics should be studied, especially several theoretical and practical aspects in understanding, for example, which data to exchange between physical and digital twin, how to synchronize the two networks, and so on, are still open, and they represent a good opportunity not only for research, but also for industry and for standardization. With this, I complete my presentation. I thank you for your attention, and you can contact me at the email that I will leave in the description of the video. So thank you again for your attention, and I look forward to getting your comments, suggestions, and recommendations.